This is a total production. Hello everyone. So this will be our first practice set for Chapter 8, where we look at nucleophilic substitution, and that's focusing on SN1 and SN2. Alright, so as we dive into the first question here, it says, which of the following substitution reactions would you expect to occur faster? Alright, identify whether the reaction is SN1 or SN2. Alright, so firstly, how would we identify SN1 versus SN2? Well, we would have to look at it and say, alright, what type of substrate do we have? Right, that would be our alkyl halides. So what type of substrate do we have? We have a primary, and we have another primary. Okay, so that in and of itself is enough for you to know, right, based off of substrates, that this is SN2. So these are both SN2 reactions. All right, now for SN2s, right, the rate of these reactions is equal or proportional to, I guess I should say proportional to, right, the concentration of both your alkyl halide, your substrate, so the concentration of your alkyl halide, and the concentration of your nucleophile. So we need to identify which is which, of course. So we've already identified our substrate, right? Here's the alkyl chloride, here's the alkyl iodide, and these two are exactly the same in every way except, right, because they both are a 1, 2, 3, 4, 5 carbon chain, and they're both primary. The only difference is the chlorine versus the iodine. All right, next up we look, so the nucleophile has to be electron rich, so that means these are the nucleophiles for these reactions. And as we look, right, they both are giving us the same product, right, because it's the same nucleophile. The only thing that's changing is the halogen, what we also call the leaving group. All right, so the rate of our reaction depends on both of these. Well, the nucleophile doesn't change for these, so it doesn't really matter. It's this that's changing. So this is what's going to affect our rate, right? The chlorine versus the iodine. All right, so which one is the better leaving group? Well, for halogens, when you look on the periodic table, right, iodine is way down at the bottom, right, which means it's bigger, right? So this is a bigger leaving group. So what does that mean? Well, if that's a bigger leaving group, that means it's going to be easier to break this carbon halogen bond, right? So this bond is easier to break. So bigger leaving group, easier to remove. So that means that this second reaction right here, this is our faster reaction, okay, between the two. All right, next up, it says, which of the following substitution reactions would you expect to occur faster? Identify whether it's SN1 or SN2. So let's identify the 1 or 2 first. All right, so when we look, we have a lot of similarities in our substrates, but yet again, it's a bromine versus a chlorine. The nucleophiles are the same, and the products are the same. So the only thing that changes yet again here is our leaving groups. Okay, those are what's changing. Now, when we look at these guys, right, based off the carbon that these halogens are connected to, right, it's got 1, 2, 3 other carbon connections. 1, 2, 3 other carbon connections. So that tells us that both of these are tertiary, okay, which means there's only one option, right? When it's methyl and primary, it's always SN2. When it's tertiary, it's always SN1. Right, secondaries are kind of iffy, right? But it's always easy for the other scenarios. So these are SN1, both of them, because they're both tertiary substrates, right? Now, with this, what does that mean? Well, when we go back and look at the rate for an SN1 reaction, the rate is proportional to what? The rate is only proportional to your alkyl halide, not your nucleophile. All right, that's important. That's an important distinction to make here. All right, now, when we do this, that means it doesn't matter. Even if these were different, it wouldn't matter about the rate. okay, based off of our rate equation. Now, why is it that the rate of an SN1 is only dependent on your alkyl halide or your substrate? That's because the first step of this reaction requires the bromine to leave, requires the chlorine to leave. So both of these have the exact same intermediate here. This tertiary carbocation, right? And this is why SN1 is almost always going to happen with a tertiary, because it's going to make the most stable carbocation that we know of. All right, now from here, what does that mean? Well, same idea as what we just did here in question number 1. The only difference is our leaving group here. So which one's a better leaving group? The bigger one, right? So bromine is bigger. Therefore, this will be the faster reaction. Okay, it's going to be easier to break the carbon-bromine bond than it is the carbon-chlorine bond. All right, so this one's faster. All right, and a third one here. It's another rate question. So what would happen to the rate of each reaction below if you were to double the concentration of the nucleophile? All right, so when we look at these are both our substrates, and now they're different. This is so when we look at the carbon that has the bromine on it, it's got 1, 2, 3 carbon connections. So this one is tertiary, right? Which tells us what? That when it follows a reaction, it's going to follow the SN1 reaction model. Here we have a bromine, and the carbon that it's connected to only has one other carbon connection. So this is a primary alkyl halide, which means it's going to follow what? The SN2 reaction. All right, so now it wants to know for each one of these, when we double the concentration of our nucleophile. So this would be our nucleophile for the first one. And then when we look at these two, which one of these is definitely a stronger nucleophile? Remember, anytime you have an ionic compound, right, break that up into its individual ions. This makes sodium plus, and then it makes, if you recall back in Chem 1, Chem 2, you called this polyatomic ion cyanide, so this is sodium cyanide. So that's the nucleophile for the second reaction. All right, now, why did we go through all this process? Identify if it's SN1, identify if it's SN2. Well, because we just talked about here, right? Remember, your SN2 reaction is dependent on both the substrate and your nucleophile. However, in an SN1, your rate is only dependent on your substrate. Okay, so what does that mean? If it's an SN1 reaction, we don't care about the nucleophile if we're talking about the rate. So for this one, our tertiary SN1, right, it doesn't matter. So if we double the concentration, I'm going to say no change in reaction rate, right? And that's all because the rate only depends on this guy, our alkyl halide or substrate. All right, on this one now, we know that for SN2, the rate is proportional to both your alkyl halide and your nucleophile. So when we double the nucleophile here, what do? Proportionality would say we double the rate. So here we would double the reaction rate. All right. Okay, next up we have some actual give me the products of these reactions. All right, so this will require that we look at these things from, first we're gonna say, hey, let's give an order of operations. First, determine what type of substrate you have. Is it tertiary? Is it secondary? Is it primary? Or is it methyl? All right. From there, right, what does this tell us? In step 2, tertiary is going to be SN1, and then your primary methyl is going to be SN2. For secondary, it's going to require a little extra. So I'm just going to circle this and put extra. At that case, that means we're actually going to have to look at the nucleophile to tell us if it's going to follow an SN1 or an SN2. All right, and then from there, we just do the mechanism. Okay, now for each one, let's look. So when we look at our leaving group here, our chlorine, right? This is a 1, 2, 3. That is a tertiary substrate. So we automatically know that it's SN1. So what does that mean? That means in the mechanism for an SN1, the first step is you always create the carbocation. So in order for that to happen, the leaving group's got to go. So the first thing you're going to see in your intermediate here is a tertiary carbocation, right? Now that you've made that, your nucleophile here, right, that's our nucleophile, it can attack. And what's going to attack specifically is going to be one of the lone pairs on the oxygen. Boom, boom. All right, now, here's the deal. When this attacked, it attacked a trigonal planar carbon. So this oxygen could attack from the front of this carbon or the back. So you actually are going to have a racemic mixture. All right, so what I'm going to do is I'm going to show that, and then say plus racemic. Okay. All right. Now from here, we're not done yet because this oxygen is positively charged now, and the good thing is it has a hydrogen on it, and those tend to be easier to remove from oxygens. So, in order for this to happen, there was a chloride ion that we kicked off before, and so some might say, "Hey, we're gonna that chloride ion is gonna come and take it." Now, one of the reasons I avoid that is because that creates a very strong acid, and reactions prefer to consume strong acids, not produce them. So the real alternative here is you have a ton of ethanol, because this type of reaction, SN1 reactions, tend to be called solvolysis. So what you can think of it as like you have 1,000 of these molecules for every one of your alkyl chloride. And so what does that mean? Probability would state that means also I'm going to have one of these to snag a proton versus 1,000 of these. So which one's most likely to grab it? 1,000 to 1, right? So the ethanol. So what we would see is that the ethanol here would take that proton and give us this product, and sorry y'all, I know it's getting a little cramped, and this product. So you would have this racemic mixture of diastereomers. Okay, that's always a problem with SN1. You have to consider if you're going to have two different products. And so since we did create a new chiral center here in our product, we are going to have this option, right, of a racemic mixture of something, whether it's enantiomers or diastereomers. All right, I'm going to draw a line here so that I don't bleed into stuff. All right, here we have a secondary substrate. And so remember, with secondaries, we have to kind of decide. It's going to require a little extra work. So with secondary, we have to now look. We can't say if it's SN1 or SN2. We have to look and see what the nucleophile looks like. And in this case, our nucleophile is this, N3-, right? Because that's an ionic compound. So this is our nucleophile. Now, in this case, if your nucleophile is a part of like an ionic compound, it's doing substitution, it's going to prefer to do the SN2, all right? If what you really want is something like, if it's going to be SN1, you want something like this. The nucleophile here was like what we call a polar protic solvent. So it's protic, right? It has a proton on an oxygen. So if the nucleophile was something like methanol, ethanol, or even water, these three could be used to do an SN1, right, where you have a hydrogen bound to an oxygen. But we don't have that here, so this is really going to act just like a nucleophile to do the SN2, okay? All right, so that means that this azide, that's what it's called, N3, this azide will attack and kick the chlorine off. Now, with an SN2, this mechanism is specific. You have to think about where your leaving group is, the chlorine. In this case, it's in the back of the molecule. So when N3 comes to attack, it can only come in from the front side to kick off the chlorine. So that means you are only going to have one product, specifically that. Right? That is all you're going to make. Okay. All right. Next up, we have an alkyl bromide, and this guy only has one carbon connection, so that's a primary. All right. So in a primary, the only option is SN2. So now that's an ionic compound, right? You see a metal and you see OH. So your nucleophile here is hydroxide. All right. Now with this, you're going to see pretty much a similar trend. The negative oxygen is going to attack the carbon to then kick off the bromine. Now you notice here there's no stereochemistry because this isn't a chiral center. So it doesn't matter about us doing the dash or the wedge in the product, because when we look at the product we make, there isn't a chiral center here, so it doesn't matter, right? You can just, this is the product and you're done. All right, next, what do we got here? We have a tertiary. All right, yeah, so that's your bromine. So there's the carbons connected to. You got 1, 2, 3 connections. So you have a tertiary. So what's going to happen here is this will follow the SN1 mechanism, and you're going to kick the bromine off first to make your happy little carbocation. All right, and now your nucleophile can attack. So remember, you see a metal. So really your nucleophile is that. Okay, you have this negative oxygen. So you're going to have that attack the positive center, and what's it going to attack? From both the front and the back of the molecule. So you're going to have a racemic mixture you're going to have a racemic mixture of products, right? So one where there's a dash on the ethyl and a wedge on the oxygen, and then, all right, I'm going to keep the ethyl going the same direction. So now the ethyl has a wedge. My wedge is a little extreme. And then you've got a dash on your oxygen. All right, so you would make this racemic mixture of enantiomers. Okay, and lastly, we have an ethyl iodide. Well, that's a methyl group, right? Because that's only that carbon has no other carbons on it, so that's a methyl alkyl halide. So it's also going to do only SN2. And so this is just a direct nucleophile attack and kick off the iodide. So if I elaborate just a little bit, it's going to look, right? I'll show the bond here. It's going to look something like this. And so your nucleophile, yet again, something that looks ionic, right? What's this going to look like? You have a positive sodium, which means you're going to have a negative sulfur. So your negative sulfur here is going to attack the carbon, kick off the iodide. All right, and of course there's no stereochemistry to consider, so you're just going to have SCH3. Right, you're just going to have that as your product. Okay. All right, hopefully this helped. You guys stay weird.